Hi, my name is Donnya Ajdari, and my group members are George Alexopoulos, Charles Kantlehner, and Janani Ramakrishnan, and we're going to be going over CMOS amplifier design. So just as a brief overview, we're going to be designing an operational amplifier using CMOS design using the following parameters, some of them including gain, slew rate, power dissipation, input and output voltage swings, bandwidth, and the noise performance. So here are some of the parameters including threshold voltage and current, the K and kappa values, as well as the early voltage parameters that we use to calculate the theoretical values as well as in our simulation of our circuit. So here we have the folded cascode differential amplifier. Here we have the differential pair. Here we have the cascoded bias transistors as well as 3 sets of cascoded current mirrors. The first being this at the top, the second being this on the side, and the third being the one on the right bottom.
In order to bias the operational amplifier, we use a bootstrap current source. The voltage from the P FET here is used to bias the P cascode, and the voltage from the N FET here is used to bias the N cascode. These two MOSFETs, whose drain and gate are connected, have a W over L ratio of 1 over 50, which is essential for subthreshold biasing. The MOSFET here has a W over L ratio of 8. This shows the picture of the complete amplifier. Here is the differential amplifier we have used, and this is the bootstrap current source which is being used to bias this amplifier. The P FET here is used to bias the P cascode, and the N FET here is used to bias the N cascode. To calculate the gain of the operational amplifier, we can use the formula Gm times R0. We consider this branch right here. The R0 for this branch is given by Gm times R0 square for this P cascode and Gm times R0 square for this N cascode. Since we have a P FET differential amplifier, we need to multiply this by the transconductance of the P FET. On doing that, we get a gain of 112.9193 decibels theoretically. Our simulation gives us a gain of 103, which is well above the requirement of 100 dB. Theoretically, the 3 dB frequency is given by 1 over 2 pi RC. When we plug in the required values for R and C, we get a theoretical 3 dB frequency of about 969 Hz. This is in agreement with the required bandwidth of 1 kHz. A similar situation is obtained from the SPICE simulation as well.
So here we have the common mode rejection ratio. On the left of the graph we have the common mode gain, the differential mode gain, and the actual ratio between the two. And on the right we have a theoretical calculation for CMRR, which comes out to around 122 dB, and a simulation that comes out to around 104 dB. The differences could be explained by the fact the simulation has to take into account EKV model effects. Here we take a look at the input voltage swing. On the top we have the voltage of the bias transistor, and then on the bottom the voltage of the cascode transistor, which follows the output. As it follows the output and gets close to the bias transistor within 100 millivolts, it crushes the bias transistor, and this is where the swing ends. Theoretically, our voltage swing should go from 0 volts to 1.81 volts, and our simulation shows that it goes from 0 volts to 1.804 volts. Here we look at the output voltage swing. The minimum voltage is 24.7 millivolts and the maximum is 2.48 volts. Theoretically, the way to calculate the swing is to remove 2 drain saturation voltages for the cascoding transistors from ground and from VDD. Our theoretical voltage swing is 2.1 volts, which is well above the requirement of 1.8 volts. The simulation says that our voltage swing was 2.46 volts, which is well above the theoretical. Here we'll take a look at the slew rate. The requirement is 100 volts per microsecond, and the current from this requirement is 10 microamps for the biasing. The resistance needed in the bootstrap current source for this bias current is 5.36 kilo ohms. For the simulation, because we needed to fix our stability with phase margin, we had to add capacitance totaling to about 3.6 picofarads. So the new slew rate calculation from this is 2.78 volts per microsecond. As we can see from the step response, the actual slew rate was 4.56 volts per microsecond.
In order to find stability, we must first find the phase margin. To find the phase margin, we find the phase at unity gain. Then we subtract this from 180, which gives us a phase margin of 46.2286, which is greater than the 45 degrees, which means it's a stable circuit. The power dissipation for this circuit was required to be under 0.15 milliwatts. We know that for our theoretical calculations, our I bias was 10 microamps, our VDD was 2.5 volts, and with 8 branches in our circuit, our power dissipation was 0.2 milliwatts. Our simulation was very close, except the I bias was 81.9 microamps. We found this by probing the output of VDD for the bias current. This was a necessary design trade-off to achieve the gain. The noise performance for this circuit was required to be under 40 nanovolts root hertz. For multisim, we found the output referred noise. To relate this to the input referred noise, we used the equation square root of output referred noise over bandwidth, all divided by the negative 3 dB gain. This gave us 23.17 nanovolts per root hertz, which is a great comparison to our requirement because we are under it. To find the area of our circuit, we take the width times length of all of the transistors and add them up and multiply times 2. This gives us a total area of 111,744 microns squared. Comparatively, this is less than the cross-sectional area of a mechanical pencil lead.
This operational amplifier design is actually very efficient because it meets almost all of the specifications. The idea of using a folded cascode differential amplifier biased with the bootstrap current reference is good because it has a very high gain. However, the folded cascode amplifier does not always meet the power specifications. Tweaking the folded cascode a little bit would help us reduce the power dissipation while maintaining a good gain.